Now we're going to take a closer look at cycloalkanes, and you'll find we'll spend a fair amount of time on cyclohexane, but we'll talk about the others in general here first. We'll introduce a new term here called ring strain. So if we take a look at cyclopropane real quick, so cyclopropane, if you look at a equilateral triangle, would have bond angles of roughly 60 degrees. We'll find out, with an sp3 hybridized carbon, those bond angles want to be 109.5. We have a problem here with that disparity, and we call that angle strain. So in this case, you'll find out that there's even papers reported that cyclopropane actually has bent bonds with this crazy angle strain, and cyclopropane is much more reactive than all the rest of your alkanes you'd ever deal with. Might do some reactions that alkenes do, as we'll find out in another chapter. But in addition to this angle strain, it turns out if you look at cyclopropane, if you were to look down any one of these bonds, so position your eyeball right here and look right down this carbon-carbon bond, you'd find out that the two dashed hydrogens are perfectly eclipsed, the two wedge hydrogens are perfectly eclipsed. It's in an eclipse conformation. Being in an eclipse conformation would also have steric strain, the atoms are as close together as possible, and torsional strain, again, the bonds are as close as possible as well, so we get repulsion between the electrons in those bonds. So the combination of those three things, angle strain, steric strain, torsional strain, and those combination make up what we call ring strain. And as the rings get bigger from 3 carbons up, you'll find out we get less and less ring strain up to a point. Notice in cyclobutane here, so your bond angles are close to 90. It turns out this thing's not perfectly planar in an attempt to avoid some of those perfectly eclipsing interactions, and bigger yet in cyclopentane. And then finally in cyclohexane, we'll find out that in one of the conformations of cyclohexane, we can get those bond angles really close to 109.5 degrees and effectively have almost no ring strain whatsoever. It turns out once you go bigger than cyclohexane, though, that your ring strain begins to grow again. So it turns out cyclohexane is kind of like Goldilocks for having no ring strain. But bigger or smaller, you're going to have some ring strain associated with that. And you should know that especially cyclopropane here, he's got the most ring strain per carbon of any of the cycloalkanes. So now we're going to take a more detailed look at the conformations of cyclohexane in particular. The conformations of the other cycloalkanes are not that important, but for cyclohexane, you got to be intimately familiar with a couple of its conformations. So you'll hear things like the boat conformation or the twisted boat, and you should be familiar with those names, that they exist. They're types of conformations, but they're not the most important things in the world. The boat here, you might be familiar with the fact that it's got 2 what we call flagpole hydrogens coming off the ends of the boat, and that there's steric strain associated with those as well. But that's about all I want you to know about the boat. Again, just be familiar that the boat conformation is one of the conformations that's higher energy. The twisted boat, higher energy conformation as well. But the big one we want you to be familiar with are what are called the chair conformations. And we're going to talk about what are referred to as equatorial positions and axial positions. And we'll find out every carbon in the ring has both one equatorial and one axial. Let's take a look. So let's take a closer look at the structure of cyclohexane here. If you look at it overhead here, we might call this the overhead planar view. Cyclohexane looks like you can see the hexagon, but you don't realize that it is not a planar structure until you kind of look at it from a sideways perspective. And it's this sideways perspective we look at when drawing the chair conformations. So we have the head of the chair here, and the foot of the chair here, and then the 2 arms of the chair here. Now if we rotate it 1 carbon over, we can adjust who we call the head and the foot. And so in this case, now we call this guy the head and this the foot, and these would be the arms. So there's a little bit of arbitrariness, but you'll see that we've got 3 sets of parallel lines. We've got parallel lines here, we've got parallel lines here, and then we've got parallel lines here, and that's all part of drawing your chair conformations. Now it turns out we also have 2 different types of positions. I've got them diagrammed here in pink and green, and the green one here are what we call the axial positions. They point straight up and straight down, just like your axial skeleton, your skull and your spine. So in this case, then we have the equatorial ones that kind of go around the molecule, around the equator, so to speak. So and again, if you look at it from the top view, you can kind of see them going around the equator. So and every other one slants down and then up. And so the equatorial ones here don't experience any significant amount of steric strain, but the axial ones, it turns out, if you look at them, these 3 all point up and are parallel to each other, and so there's some torsional strain as well as steric strain associated with that. So then the ones on the bottom do the same thing. On the bottom here, these 3 point down in green, experience the same thing. And since it's every other carbon, we refer to those as 1,3 diaxial interactions. So if you also look down one of the bonds here, and we're going to look down this bond right here, you'll see that in cyclohexane we're at a perfectly staggered arrangement. So and that also leads to the stability of the chair conformation. You'll also notice that with the axial position, you have a gauche interaction with this carbon right here. So that's a gauche, 60 degrees apart. But for the equatorial positions, so in pink here again, there's no gauche with the carbons in the ring. They're pointing exactly opposite the carbons in the ring. And that's another part of those 1,3 diaxial interactions. Sometimes people will mention that there's gauches there, and there's actually a couple of them for each, depending on which bond you look down. We can look down this bond as well and see that this guy's got another gauche with this carbon up front here as well. So, but whether or not we look at those or not is not the biggest concern in the world. Some people just swallow them up and just call them 1,3 diaxial interactions. But it is for this reason that it is more stable for a substituent to be in an equatorial position as compared to an axial. So let's take a look at our chair conformation again from the side view. So in this case, we got our head and we got our foot. And if you want to do the chair interconversion, so take your foot and flip it up. And if all we do is just flip it up, we'd have our boat and there'd be our flagpole substituents. So but then take what used to be the head on your left and flip it back down, keeping those arms parallel. Not the easiest thing in the world to do. In this case, I got a new chair, new head, new foot, but if you notice the difference in positions, so now it's all the pink ones that point straight up and straight down. They're the new axials, and the greens are now all equatorial going around the equator, so to speak. So, and again, if we flip it back, flip the foot back up, so, and I'll flip the foot down, and notice all the bonds rotate just a little bit, so that it's arranged in such a way that now again all the green ones are back to being axial and all the pink ones go back to being equatorial. This is your chair conformation. You should totally build a model of this at least once. You should totally do the chair-chair interconversions and see how everything axial flips to everything equatorial. One thing to note, when everything axial flips to everything equatorial, let's focus on this one right here. So this guy right here, that's axial right now in green. When I flip it to the other chair, so in the other chair, he's now equatorial right here, but he still points up. Now he's not straight up, he's still slanted up, but he still points up, and that's important, as we'll see when we start talking about cis and trans and things of this sort in just a little bit. So let's talk a little bit more about drawing chair conformations. So you draw a cyclohexane, you find your first ones are probably going to look pretty ugly, but you'll find that we've got 3 sets of parallel lines. That one is parallel to that one. That one is parallel to that one, and those two are also parallel. So, and if you start from there, I like drawing the axial positions in first myself, and if you go to either of the highest points on your diagram here, draw an axial straight up, so, and then they alternate all the way around ring, so straight down on the next one, straight up on the next one, straight down on the next one, straight up on the next one, straight down on the next one, and those are your axial positions. So if you notice when you draw a normal overhead planar conformation here, that every carbon has a wedge and a dash. And we're looking at a sideways view here with this chair conformation, and so the wedges point up and the dashes point down. So if you look at our axial positions that we've drawn, half point up and would correspond to like a wedge, and half point down and would correspond to a dash. If your axial is the wedge pointing up, then your equatorial has to point down. You'll also notice that we can kind of cut this thing in half here. So, and anything pointing to, any of the 3 equatorials on the right will slant to the right, and any of the 3 equatorials on the left would slant to the left. So for this guy here, his axial points up, so his equatorial is going to point down. So, and it's on the right-hand side, so it'll be down and to the right, and there's your equatorial. This one, the axial is down, so the equatorial is up, and it'll be up and to the right. This one, the axial is down, and so the equatorial will be up and to the right. On this side, this guy, the axial points down, so the equatorial will be up and to the left, down and to the left, down and to the left. So, and there's your equatorial positions. You want to practice that. You should be able to draw all the axials and all the equatorials on any chair conformation presented to you. And one thing you want to keep in mind again is that when you do the chair interconversion, everything axial becomes equatorial and everything equatorial becomes axial. Let's have a look. So now we want to take a closer look at these 1,3 diaxial interactions we spoke of earlier. And again, these are why we attribute the equatorial position for a substituent being lower energy than the axial position. And so if we put a chlorine on the molecule here, we'll have 2 chairs in equilibrium together. And when the chlorine is equatorial, it'll be more stable than when it's axial. And as a result, it won't be a 50-50 mixture in equilibrium here. It'll be 70% with the chlorine being equatorial. We'll find that the larger this substituent becomes, the more it's going to take preference for it to be equatorial rather than axial. So if we look at the methyl group actually is going to take up a little more volume, a little harder group, if you will, a little harder substituent, we say. But in this case, it actually prefers the equatorial 95% to 5% for the axial here. So even bigger difference. And once you get to a T-butyl group, this big group, you know, with 3 methyl groups coming off it, so you get 99.99% to 0.01%. Huge preference for the equatorial position. It's effectively locked in the equatorial position, we like to say. So the big things you look for when you're trying to draw most stable chair conformations or lowest energy chair conformations. So it's lower energy when larger groups are equatorial, and lower energy when more substituents are equatorial. And which one's more important depends on really what you got. If you got a T-butyl group on your molecule, by all means, make sure he's equatorial, in preference even to the more substituents being equatorial, to get your lowest energy conformation. But otherwise, it's a little interplay between the two, and it takes a little practice to get used to that, but both play a role. Larger groups, you want them to be equatorial, and you want more substituents in general to be equatorial to get that lowest energy conformation. So we want to take a minute just to delineate the difference between cis and trans when we're talking about cyclohexane. So there's usually a little bit of confusion here on what that exactly means. Now in the overhead planar conformation, it's not too difficult. Cis here means that both your substituents, whether they're identical or different, are either both wedged bonds or both dashed bonds, and that's cis. What that translates to when you draw your chair conformation, since we don't draw wedges and dashes, is what direction they point. So if you notice, this axial position points up, this equatorial slanted up, and when they're both up or both down, that's what cis actually means. So it does not necessarily mean both axial or both equatorial or anything of the sort. Sometimes it does, sometimes it doesn't. What it always means is both up and both down. So notice here, both up happen to be one axial and one equatorial. Here in the next one, both pointing up means they're both axial. In the next one here, so one's down, the other's down. That's cis again. One's axial, one's equatorial. So again, with axial versus equatorial, there's no rhyme or reason. Well, I shouldn't say there's no rhyme or reason, but there's no ultimate pattern that is always true. But for up and down, that's the thing. Both up or both down, that's cis. And this last one, they're both equatorial, and they both point down. But the key is that they're both down. That's what makes it cis. If we look at trans then, trans means one wedge and one dash if you look at the overhead planar conformation. But on the chair conformation, that refers to up and down again. One up, one down, that's trans. One up, one down, trans again. One down, one up, trans, and then again one up, one down. You'll see in some of these conformations we've just done for the trans versions, some had both in the same type of position, axial versus equatorial. Some had one axial, one equatorial. Again, for trans, it always means one up and one down. And sometimes that happens to mean both axial, both equatorial, and sometimes that happens to mean one axial, one equatorial, but it always means one up and one down. You should definitely know the difference here between cis and trans and recognize them pretty readily. So one of the common questions on this particular exam is for students to be asked either to draw the lowest energy conformation or to draw both chair conformations and then draw which one's lower energy. So that's exactly what we're going to do here. So for these three molecules. So in this case, we've got a 1-4 relationship, regardless of how you slice it, who gets to be 1 and 4. And on a ring, you can start those in any place you want to. It's really your choice. A lot of people like to start on the foot or on the head and stuff like that, but it doesn't really matter. What we'll do, though, is that we should keep in mind that the wedges mean up and the dashes mean down. I mean, it could technically mean the other thing if you flip it the other way, but I'm always going to flip it this way, and I recommend you get in the habit of doing the same. So I'm going to just choose to put atom number 1 right here. I'll make him number 1. So, and whether I go around clockwise or counterclockwise, I'll get to 4 at the same position, 1, 2, 3, 4, or 1, 2, 3, 4. So in this one, it doesn't matter. We'll find out in the others it will. So, and in this case, there's an up and a down, and we want to make sure that it's in the up position to put the methyl group. Here there's a down that's axial and an up that's equatorial, and we want to make sure on carbon 4 that again, that's a wedge, so we're going to pick the up position, and that's where we'd put our 2 methyl groups. Now if we do the chair flip, we want to keep in mind how things are working here, and so where the foot is going to become the new head. This whole thing flips up, and then the whole head flips down, and so where the head used to be is now going to be the foot, and then the arms stay the arms. So if you notice, we've got the left side of the back arm, and that back arm is right here, and the left side, that would be carbon number 1. So, and then we've got the front arm here, and we've got the right side of it. So here's your front arm of the chair, and the right side of it, that's number 4, and that's where we need to put our substituents for the corresponding chair interconversion. And in this case, the down position's axial, the up one's equatorial, and we need the up position again. And notice axial became equatorial just like it's supposed to in the chair interconversion. So on carbon 4, the axial's up, the equatorial's down, and in this case we need that up position again. And so we've now got one axial, one equatorial in this chair, and we've got one equatorial, one axial in this one, and being that they're both methyl groups, these are perfectly equivalent. They're going to be in solution 50-50. There's no difference in energy between the two. One methyl axial, one methyl equatorial, same diff. Now let's go to the next one. The next one's going to be a little trickier. It's not quite as symmetrical. I'm going to make this guy number 1, and I should number around to get the lowest possible number for the next one, so we'll number around clockwise, 1, 2, 3. If we're numbering around clockwise here from 1 to 3, then wherever I choose to start number 1, and I'm going to start number 1 right here this time. So on the foot carbon, my choice again, I can start anywhere, but in doing that, I should number around the same way I've numbered here. So it's clockwise on the overhead planar conformation, so I'm going to number around clockwise to get to 2, 3, and that's where we're going to put our other substituent. So the up position here is the equatorial, the down would have been axial, so we'll put one of the methyl groups here. So in here, again, another wedge, so the up position is also equatorial. And there we go. So notice in terms of cis 1,4-dimethyl cyclohexane and cis 1,3-dimethyl cyclohexane, we'll see that there's a more stable chair conformation for cis 1,3, being that they can both be equatorial. Now if we draw the corresponding chair flip, so again, your foot now becomes the head of the chair, and then we're on the right carbon of the back arm, that's this guy here. So that'll be your positions 1 and 3. And the up positions on both of these are going to be axial positions, and this chair will not be nearly as stable, nearly as low energy as the other one we've got listed here. So, and in equilibrium, this would definitely be the lowest energy and the predominant chair conformation in solution. Finally, the last one here, also a 1, 3, and I'm just going to number it exactly the same way. And I'm going clockwise, and you know what, I'm going to put it in exactly the same positions for the fun of it here. Choose the foot and that particular arm. So, but now the first one is a dash, and that's going to point down. So that's where the first methyl group is, and we can see that's an axial position. So, and the next one here is going to point up, and that's an equatorial position. So, and when we do the chair flip, the axial becomes equatorial, the equatorial becomes axial, the foot becomes the head. It's still going to point down here, but the down position is now equatorial. So, and go clockwise over 2 positions. So, and the up position is an axial rather than equatorial, but again, it still points up. So when you do your chair flip, axial becomes equatorial, equatorial axial, but up still points up, down still points down. That's not going to change. And between these two, with one axial and again one equatorial, just like the first example, these would be present in equilibrium 50-50. There's no difference in energy between them. So if you haven't noticed the progression here, we've gone from having 1 substituent to 2 substituents, and now finally to 3 substituents on your cyclohexane. So, and here you're being asked to draw the lowest energy conformation, and you should notice that we've got a big bad T-butyl group here and 2 methyls, but that T-butyl group we should worry about more than the other 2. And in this case, if you want to draw the lowest energy, you can draw both chairs and then figure out which one's lowest energy. Or you can kind of take a strategic view of this and worry about that T-butyl group first. So in this case, I want that T-butyl group to be equatorial, no ifs, ands, or buts. He's much, much larger than those methyl groups. And in this case, I also need him to be a wedged bond, so that means he points up. So it turns out half your equatorial positions point up, half your equatorial positions point down. We need to find one of those ones that points up and start from there with this carbon with the T-butyl group. So in this case, that happens to be one of them. That equatorial points up, that one points up, and that one points up, and it wouldn't matter which of these 3 we choose. We're just going to take and choose any one of those 3. And so in this case, I'm just going to use this guy, and that's where my T-butyl group is going to go. So all my CH3s there in the equatorial position. So cool. From there, I'm going to number around counterclockwise 2 positions to get to this carbon. So 1, 2. Then from here, this is a dash, so I need to pick the down position. Notice we already had the equatorial drawn in, but that's up. The down position is going to be the axial, and so we'll put a methyl group right there. From there, we'll go down, again, counterclockwise 1 more position, so right here, and we need the up position, and we'll put a methyl group there, and the up happens to be another axial. So, and in this case, it didn't work out as well as I would have liked, but you are stuck with what you're stuck with. And we've got both methyl groups being axial, so, and the T-butyl group being equatorial, but this will be more stable than the alternative. Notice the alternative would have both of the methyl groups equatorial and the T-butyl group being axial, but again, that T-butyl group is much bigger than anything else on this molecule, and we got to worry about him first and foremost. So this is our lowest energy conformation. If we did draw that other conformation here, in this case, this carbon right here is the one with the T-butyl group, and it would now have the T-butyl group in the axial position and go over again counterclockwise 2 positions. So, and now we'd have in the down position, which just happens to be equatorial, a methyl group. So, and then one more position counterclockwise, we'd have a methyl group in the up position. Maybe I'll slant that a little better. That looks horrible. C'est la vie. And in this case, we'd have another one in the equatorial position. And so even though there's 2 equatorials and 1 axial, again, it's all about that T-butyl group. He's much bigger than those other 2. So I wanted to take this time to look at what I like to call a double Newman projection here. So sometimes we look down the bonds, and in this case 2 bonds at the same time for cyclohexane, and that's what we're going to do here. And what I want you to do is kind of take this perspective. We're going to look down this bond. So, and you can look down any 2 parallel bonds in cyclohexane. So at the same time, we're going to this bond, So this would be our front carbon, this one our back carbon. Again, this is our front carbon, this is our back carbon. So on the 2 sides, and so on the left, I've got a methyl group pointing up on the front carbon. And for the front carbon here, that methyl group, let's just switch colors here. So on that front carbon here, pointing up is a CH3, and what's not drawn in pointing down is a hydrogen. So, and then on the back carbon, represented again by our circle, we have in the down position, and that's this one right here, a methyl group, and then a not drawn in is another hydrogen that would be a wedge, so pointing here. Cool. If we go to the left-hand side, again, we've got a front carbon and a back carbon. So, and the front carbon just has 2 hydrogens. So, but the back carbon here, again, represented by the circle, so is going to have the T-butyl group, and in this case, it points more up. So we'd have the CH3, that's where the T-butyl group is. And then not drawn in, but now drawn in, would be a hydrogen. And so this would be this double Newman projection, one of the other common representations of cyclohexane you're responsible for. One thing you should note then, so is that some of the positions point straight up and straight down, and those are axial positions. But the ones that are slanted off to the side are the equatorial positions. You should also notice that if everything points up and down, so like these 2 methyl groups, you could totally see right here that one's up, one's down. One corresponds to a wedge, one corresponds to a dash, and that would be trans to each other. So those kind of relationships hold true on this kind of a representation as well. So not only can you tell who's axial and equatorial, but you can see those cis-trans relationships too. So but another one of those representations you're probably going to need to be familiar with for your course.